Hi, my name is Ivo and I'm doing research into Nikola Tesla's impulse electricity. I published my radiant half-bridge circuit in November 2020, but it does not work as I intended. There is a design flaw that I am not able to fix, but luckily the PCB still is functional. I realized the dual MOSFET PCB can now be used to simultaneously switch two MOSFETs in series, which I now use in my Tesla oscillator circuit. Let me explain what went wrong and how it still can serve its new purpose. This is the November 2020 radiant half-bridge circuit. The intention was to produce alternating unipolar impulses, but it can't as it is ringing all over the place. I will show you 3 small experiments to explain what is going wrong. Let's start with showing you the ringing of a coil at its resonant frequency, with a simple circuit using a 6-volt battery. First thing we'll do is switch a coil that is grounded, connect it up to a battery of 6 volts. We'll hook up a probe so we can see what the coil is doing, and what we'll do is make a very short connection over here. When it's connected, the L1 coil is magnetized, and when disconnected, the L1 coil will start ringing, like so. It will start with a negative voltage because we are switching the positive, which is the high side. If we would be switching the negative, then we would start with a positive voltage. So let me explain the setup first. I've got a battery here, 6 volts. I put a ground connection on it. It attaches the outside rim of the coil to the negative. And then we have the inside rim of the coil here. I've connected it to the high voltage probe. And what I will do is connect it very shortly to the positive of the battery and then disconnect it. Meanwhile, the oscilloscope will trigger and will record what is happening with the voltage on the coil. I'll very shortly tap it like this. There's a little spark. What this did is magnetize the coil, and when it was disconnected, the coil starts ringing, which is at the resonant frequency of this coil. Here you can see the oscilloscope. I've recorded what happened and zoomed in. I'll zoom out again. You can see it is ringing, and that ringing dies off due to the resistance of the coil, which transfers the resonant electric energy into heat and radiation. If we zoom in to the beginning, it's a little bit erratic, but you can see it starts off with a negative voltage, and this is because I switched the positive voltage on and off. In the next experiment, I will show you what happens when I switch the 6-volt battery on and off with a MOSFET. But first we'll take a look at the body diode of a MOSFET. Let's take a look at a MOSFET. This is the drain, this is the gate, and this is the source of the MOSFET. Now I've got something here. I did that on purpose. There is a body diode over here. This body diode is like a valve that only passes electric energy in one direction. And this body diode is always part of a MOSFET due to the way a MOSFET is being made. Normally this is not really a problem, but we will be switching a coil, and then this coil will start ringing like so. This part of the negative voltage, when the MOSFET is turned off, will not be able to pass anything because the diode is blocking the negative voltage. But here in the second half of the cycle of the resonant L1, we have a positive voltage and a positive current, and this can pass through that body diode. And then it goes up to the drain, back into the battery. And this doesn't need to be a problem, but I can produce 3500 volt impulses. So you can imagine that when 3500 volts is flying out of that MOSFET, then the power supply might be damaged. So to protect it, we place another diode over here, right before the positive power supply. This way, when that second half, when the positive voltage is passing through the body diode, it will be blocked by this diode again. To be clear, there are IGBTs without body diodes, but IGBTs do not turn off quick enough to produce proper impulses, so I only use MOSFETs. So positive power supply voltage flows through this diode, through the MOSFET, into the coil, energizes it, then the gate voltage is lowered, the MOSFET turns off, the coil starts ringing. We first have a negative voltage, which is blocked by the diode and the MOSFET, but then we have a positive voltage, which passes through the body diode, up to the drain, and there it is blocked again by this diode. Let's take a look at how this looks in a experiment. So here we have the setup with the single MOSFET. This PCB turns the MOSFET on and off by using a coax. I am hooked up to the signal generator, which produces a 50% duty cycle square wave. On this PCB also is a diode, and the battery is grounded. The coil is hooked up to the outside rim as before. The inside rim is connected to the source of the MOSFET, and then I have another lead going to my high voltage probe to see what is going on between the source and the coil. I've got another battery pack here. This is purely to provide 19 volts to the gate driver IC that switches the MOSFET. So this can be ignored. Also the electronics on top that's not connected, it's from another project. And I've got a 12 volts power supply externally for the fan. So let me turn it on and we'll take a look at the scope at what is happening. Here you can see the signal. In purple, when the MOSFET is turned on, it's high, and when it's turned off, it's low. And as you can see, when it is turned off, the coil starts ringing. This is at 53.9 kilocycles per second. So the resonant frequency is the same as before, around 1 megacycles per second. As you can see, it starts again at the negative voltage because the positive voltage is being switched. So the coil now is ringing. We do not have a single impulse. If we would want to have a single impulse, then I would have to connect a capacitor from the drain to the ground. Let me show you this. So we've seen that it remains ringing, and this is not what we want. What we want is to have a single impulse, so only a half wave, and then we want the voltage to stay 0 here on the L1 coil, between the coil and the source where we are probing it. Now, how do we do this? We have a solution for this. We can do this by adding a capacitor between the drain and the diode to ground. What this does is store that positive energy from this half. So when that half is being created, it is passing through the body diode up to the drain. It is blocked by this diode because it is in reverse. But now it can charge up the capacitor, and then all that energy is charged in that capacitor, so it doesn't appear here anymore. That's really nice. The capacitor is large enough that that voltage will never rise to a very high voltage. It keeps it very low because that's a large capacitor. Then it stays in that capacitor, it stays charged until the MOSFET is being turned on again, and then it discharges over the L1 coil again. Once the capacitor is discharged enough, the diode will open up again and the positive voltage is powering the L1 coil again for the next cycle. So the energy is fully stored and reused by using this method. Let's take a look at this. Okay, this is the new setup. I've got a capacitor here, which is a Wima MKP10 0.68 microfarads, 2000 volts DC, 700 volts AC. I connected it to the drain of the MOSFET, so it's between the diode and the MOSFET in, and to the ground, the negative of the power supply. The rest of the setup is the same, nothing has changed. So let me turn it on and show you how the signal looks now. As you can see, there is now only a single half wave, which is the impulse that I want to see, that I want to use. What you can also see is the little bump right before the MOSFET turns on again. Let me zoom into that. There's a little bump right before the MOSFET turns on again. And this bump is something I don't understand. But this is the impulse that I want to see and that I want to use. So there is no ringing anymore, and this is because when it turns positive, the body diode of the MOSFET turns on and conducts the energy into the added capacitor, and then the capacitor discharges again when the MOSFET is turned on. And this is very efficient, no energy losses, there is no excessive heating. All the energy is recycled and reused, and a powerful unipolar impulse is created. But this cannot be applied to the radiant half-bridge circuit as it has two MOSFETs. So now we have seen that we can produce a single impulse, and that's really nice. But this solution with the capacitor can't be done with the radiant half-bridge, because now the L1 coil is in between the two MOSFETs. And we still have those body diodes, like so. So now when that L1 coil starts ringing, when it starts ringing with the positive first, so this cycle, then it can pass through this up to here. And to solve this, I placed a blocking diode like so over here. But I can't place a capacitor here because that will take that voltage of the first impulse and will store it, and then I would have no capacitor at all. The same is when we switch the other MOSFET, then the resonance will start negative. And then the negative voltage will pass to the other body diode. It will go down and to here. So then I place a diode in reverse over here, but still I can't get a capacitor there. So it is not functional. And I have tried to come up with a solution for this, but there is no solution for this, at least not as far as I can see it. Maybe somebody can see it, but I can't see it right now.
And now for something completely different.
So the radiant half-bridge circuit doesn't work as expected. Luckily, all the work I put into it was not a waste, as this circuit is able to simultaneously switch two MOSFETs in series, and that is awesome. I love how this came to be. I worked very hard to get the radiant half-bridge circuit working, and then I suddenly realized it could also be used to switch MOSFETs in series. There it suddenly was on my workbench without even knowing I had solved the challenge. So to be clear, I will not be using the radiant half-bridge circuit anymore. Instead, I will use that PCB to switch two MOSFETs in series. Let me show you how that is connected. Now we have this flawed circuit design. Now we can fix it to make it into a working design again, because now we still have the two MOSFETs in series and switch them simultaneously. These squares are the gate driver ICs, and they are giving the same signal, 50% duty, and that way they will turn off and on simultaneously, very fast. And this makes it able to switch a coil here again on the bottom. We still need a blocking diode over here, just one is enough, and then we put a capacitor over it again as before to store the energy again. And then with this setup, using the PCB of the radiant half-bridge circuit, we can create very negative impulses of minus 3500 volts, as I have shown you before, because all the positive energy of that transformation, all this energy is then again passing through the body diodes of the two MOSFETs in series, is being blocked by the diode over here, and then it is stored inside of this capacitor. And then when both the MOSFETs are turned on again, then this capacitor is discharged over the L1 coil again, and the energy is reused, so it's very efficient again. And that is what I'm using right now. So here we have two PCB boards of the MOSFETs. This is the one I published, and this is the one I now use. They are both basically the same. So the radiant half-bridge isn't useful. What needs to be done to make this useful is make it into a series switched MOSFET board. And to do this, you remove the diodes from the board. And what you do is you place another connector there where the diodes are. So you have another hookup place on the source and the drain. This is for the L2 coil to be hooked up in parallel to the MOSFETs. So you need another connector here and another connector there. And what you need is to forget all about this in the middle, in between the MOSFETs. You don't need this connection anymore. So you just forget about it, don't use it, that's it. Furthermore, let me show you with this circuit board that is based on the C2M MOSFETs. What I did is hook up this coax to the board. This red one is coming from my signal generator, and as you can see, it is split into two signals that feed into the gate driver ICs. As you can also see, I placed another connector here and another connector here, so here the positive of the supply comes in, and that is this extra addition. Here is that capacitor that captures the positive impulses of L1 that pass through the body diodes of the MOSFETs. So they are coming into here and they are captured in this capacitor, which is grounded and connected to the power supply. And then we have the diode. I have two diodes in series, so the positive half wave that passes through the body diodes is blocked by this diode, and then it is stored in that capacitor bank, which are 4 times 1 microfarad 100 volts Wima FKP2 capacitors in parallel 4 times. And yeah, that's about it. That's how this all works. I placed the fans on the MOSFETs again because the energy that passes through the body diode makes it heat up a little bit, and the more the MOSFET stays cool, the better it switches. This is how you make it work. It's a small modification, and then you are able to switch very high voltages and produce very high voltage impulses. Like what I'm doing here is 3.5 kilovolts maximum, and yeah, to me it's very impressive. I'm very happy that I'm able to do this with this beautiful designed circuit board. My YouTube channel has almost reached 10,000 subscribers, which makes it possible to link merchandise to this channel. And I was wondering if you would be interested in that, and if so, what items would you like? Let me know in the comment section below. Please hit that like button, subscribe, and if you wish to fund my open source research, you can leave a donation on my PayPal account, which is listed below this video. That's it for now. Thank you for watching and see you next time.